out sections 11.3 and 11.4. So let's just say that we want to do like the integral from 0 to 3 of 30 dx. So if we want to do that, what's the antiderivative of 30? 30x, very good. And then we'll evaluate this at 3 and 0. And get like 90, right? Now, if we think about this graphically, like we have an xy axis here. Say we go by tens. So like this is the line, y equals 30. And if we're looking between 0 and 30, we've made basically like a 3 by 30 square, right? Yes, Joey? You just tack the x on to the end, but our antiderivative rule is this guy. Yeah. So you didn't do that? I did do that. Oh. Because it's like x to the 0, right? It's like 30x to the 0. Yeah. So I added 1 and then divided by 1, or added 1 to the exponent and divided by 1. Is that okay? Okay. And guess what the area of that is? So it turns out that the geometric interpretation of an integral is going to be the same as the area under the curve. So derivative is slope of the tangent line. The integral is the area under the curve. Everybody's okay with that? So another way we can compute an integral then is geometrically. So let's look at a couple of examples where we can do that, even for functions where we don't know how to find the antiderivative. Oops. So for each function, we're going to draw a sketch of the function and shade the area between. Thank you. Allie, it's for you. It's your early dismissal card. Shocking, like you didn't know that was coming. Then we're going to use geometry to find the area of that shaded region, and then we'll calculate the value of the definite integral for that same interval. Okay, so we'll start with the first one. This is really easy. I don't need a calculator to help me graph. F of x is equal to 3. So if I graph y equals 3, there's that. And then from 1 to 5, we'd have that. So that's my shaded region, right? So this is just like a 3 by 4 square. So we can say the integral of 3 from 1 to 5 dx is just going to be 3 times 4, or 12. And if I did this as a definite integral, we would do, just basically what we did before. And get the same result, right? Let's do the next one. So that was y equals 2x, and we were going from 0 to 3. So if I graph that, we're going 1 over and then 2 up, 1 over and then 2 up, and like 1 over and 2 up. We're going from 0 to 3 then. We're talking about that's my area. What shape is that? How do you find the area of a triangle? 1/2 base times height. The base here is 3 and the height is 6. So we get 9. The integral from 0 to 3 of 2x dx, well, the antiderivative of 2x is going to be 2x to the 1 plus 1 over 2, or just x squared. And again, I get the same result. I'm going to actually skip down to D here. Oh, no, I guess I should probably do... No, I shouldn't. I'm just skipping down to D. So here my function is the square root of 4 minus x squared. Now, you might need to graph that on your calculator to know what the picture is going to look like. I don't. What does that shape look like to you? Looks like half a circle. What's the area for a circle? Pi r squared. So the center of my circle here is at 0. So like that's my radius. So we get 2 pi for the area. Now, if I'm asked to do the integral of this, do we know how to take the antiderivative of the square root of 4 minus x squared dx? Can we find the antiderivative of that with what we know? God bless you. Nope. So what do? We just type into our calculator. Remember, we showed you guys how to do this last time. So I do math and then command 9 on my calculators, fn int. Then I can just type it in just like it looks like on my sheet of paper and press enter. Take us a minute and spits out that decimal. Do you think that's the same as 2 pi? Let's check. Because 2 pi was our geometric answer. Yup! What do you guys think on this? Is everybody okay so far? What if we ask you to do something like this? Find the area enclosed by the curves f of x equals square root of x plus 3, g of x equals negative 2x times the quantity x minus 2 cubed, and the x-axis. Oh no! How are we going to do that? Well, I would want to start by looking at a picture. So I'm just going to type in the two functions. And I'm going to set my window. This thing starts at negative 3, right? Because that's anything less than negative 3, I'll have a negative under the square root. So I'll start 1 unit before that just so I can see cleanly where it starts. And this guy crosses the x-axis at 2, so I probably need something bigger than 2. Maybe I'll just go negative 4 to 5. Well, let's do 4. They're nice and symmetric. We want to be enclosed by the x-axis, so I don't need much on the min side. And this guy at 4 is going to, if I plug 4 in, the biggest that's going to be is the square root of 7, which is still less than 3, so probably 4 here is going to be sufficient. Just trying to pick a decent window so I can see this thing. So there's my first curve. There's my second curve. So the area I'm looking for is like that region, right? Everybody's okay with that? So what I notice is that, well, up to this point here at this intersection, I'm just needing the area under the square root of x plus 3. And then after that point, I just need the area under negative 2 times the quantity x minus 2 cubed. Did you guys see that? So I just really, like, I can say, okay, well, this is going to be like the integral from negative 3 to something of f of x dx plus the integral of that something over to 2 g of x dx. I just need to figure out what that something is. And geometrically, what I'm saying is that something is the intersection of the two curves. So I'm going to just use my calculator to find that. So second, trace, intersect command, enter, enter, enter. That happens at x equals 1. So now I'm good. Is everybody okay with how I broke that area problem up into two integrals? Yes, Joey? So I looked at the picture that I'm looking between the two curves and above x equals 0, so the x-axis. So the first curve started at negative 3, ended at the intersection. The other curve started at that intersection and ended at 2. Does that feel okay? Okay. So I'm just going to type this into my calculator now. So I'll do math fn int negative 3 to 1. And rather than typing that function, and again, since I already typed into the y equals menu, I can just do vars, y vars function, and pick y1. And then I'll add to it the other integral, so math command 9 1 to 2, and then I'll go and put y2 there. Again, I could type the thing in over But since I already typed it in once, I don't need to do it again. So I do that, and I get 5.83-ish. What do you guys think? So far, so good? So some of these problems, you can find the areas geometrically, right? Fine to do that. Some of the problems, you'll kind of just set up with your calculator. Fine to do it that way. Let's do a story problem, then we'll move on to the last section, 11.4. This is a ramp for a skateboard holding a side piece is modeled by the area enclosed by the y-axis, the x-axis, the function f of x equals 1, and the curve g of x equals 3 minus square root of yada yada yada, with all measurements in meters. Use your GDC to sketch the shape of the piece of the coordinate on the coordinate plane using the equations given. Okay, well, all right. So I need f of x equals 1, and then I need 3 minus square root 9 minus x minus 3 squared. Oops. Close the parenthesis. Okay. Now I'm going to reset my window here because it's between the x and y axes. So I'll just take -1 as the x min and the y min. The x max, well, has to be under y equals 1. So I'm going to just change that y max to 2. And then the x max, I'm probably good at, well, when x equals 6, I have 3 inside here, and 3 squared is 9, and 9 minus 9 is 0. So that's probably as big as that can get. So let's make that 6 then. Or I'll do one more. We'll do 7. And then we'll just take graph and take a look at what we got here. Oh boy, I think I put stuff in the wrong spot. Yep. I wanted that to be 7. That could just be like 2 or something. Sorry. Okay. So the piece that I'm talking about is that piece right there. Does everybody kind of see that? That's like the side of my skateboard ramp. You guys good? So if I want the area of that, up until here, it's just the area under y equals 1. And then after that, it's just the area under g of x. You guys good with that? So I just need to find that area. So from 0 to something, it's just f of x dx plus something to, what was it? I guess I didn't look at what that was. Looks like 3 in g of x dx. We just need to find what that something is. Again, to find that, I'm just going to find the intersection of the two curves. So second trace, intersect command, enter, enter, enter. Oops, wrong intersection. Intersect command, enter, enter, and then I guess I need to give it a better guess than that. That should be close enough to find the one I want. There it goes. 0.764. And now it's just calculator time, my dudes. So I'm just going to steal the previous input and just update the bounds. Oops, I meant to press enter. So I get about 1.45. What do you guys think? It's okay. And in the weirdest choice of section ordering, 11.4, we're going to talk about approximating that area under the curve. So let's say that instead of having like a known function, what I have is just like a table of values. Like I was doing an experiment or something. So I can like take some measurements, and maybe if I wanted to, I could graph them. If I wanted to then calculate how much flow went through this pipe or whatever in those 8 hours, that's equivalent to finding the area under the curve, but I don't have a curve. So kind of what I'm going to think about doing here is I'm going to think about each of these as like a trapezoid. And I'm going to find the area of each of these trapezoids and then add those 3 areas up. And that'll give me approximately the area under the curve. I mean, the curve is probably some, something like that. So it's not going to be exact, but it'll be a good approximation. So remember, the area for a trapezoid is 1/2 B1 plus B2 times the height. So if I look at this first trapezoid, B1 is that side, B2 is that side, and the height is that piece. So T1 is going to be 1/2 times 12 plus 17 times 2, right? So the heights are just going to be the y values, and the h is going to be the difference in the x's. Is everybody okay with how I filled that in? T2 is going to be 1/2 17 plus 18 times 2. And then oh my goodness, I missed the trapezoid here. Great googly moogly, guys. Look, I missed that one. So this one should be T1. This is T2, this is T3, this is T4. I had 4 trapezoids there. Eep! So that's what I really did on T1. So there's T2. There's T3. And there's T4. It's okay. And then we'll just add up those guys together in our calculator, and that'll give me my area. Oh, and you know what I'm going to do here to make it easier typing in my calculator? I'm going to notice that those guys all just cancel out, right? The twos and the 1/2. So not that you need to do that, but boy, howdy, that makes it easier to type into your calculator, because you cut down on like about 1 million keystrokes doing that, and I am all about making my life easier. So when I do that, I get 129. I guess that would be like cubic meters, because the flow was in, well, 120, I guess 129,000 cubic meters, because it's in thousands of cubic meters per hour is the rate. Let's do another example, and then or two, and we'll be done. How's that sound? What do you guys think? It's all right? This should be relatively easy, right? Conceptually, it's pretty clear. Like, it's nice to have a picture to look at what you're doing. The arithmetic is pretty easy, because all you're really doing is finding adding up some areas. All right. Yeah, this is another case of bad editing by our textbook. It says use the trapezoid rule to find the area, or find the value for the integral from 0 to 8 of the absolute value of 2 to the x minus 8 dx using trapeziums. Well, item number 1, the textbook means that number to be a 4 based on the work that they show to go with it. So somebody edited this and then was like, this is too much arithmetic. Let's make this just 4 instead of 8, but they didn't change the problem to make it the 4. Real on brand for our textbook here. So what I'm going to have here is I'm going to call f of x just that absolute value of 2 to the x minus 8. So my first trapezoid is going to be 1/2 f of 0.8 plus f of 0 times 0.8. So trapezoid 1 is going to go from 0 to 0.8. Trapezoid 2 is going to go from 0.8 to 1.6. T3 is going to go from 1.6 to 2.4. T4 is going to go from 2.4 to 3.2. And then T5 will go from 3.2 to 4. Everybody feel okay there? Now I can compute each one of these values separately into my calculator, but I don't want to do that. The way that I'm going to do this is I'm just going to type this f of x into y1, and then I'm going to use my calculator to do like y1 of the value, just so I don't have to just do all the computations, write them down, and then recopy them into my calculator, because it's just like kind of annoying. And I'm expecting like some cuckoo decimals in here too. And the calculator just store all the decimal for me. So to do the absolute value, I press math and then go over to the number option. The first command there is ABS. That's short for absolute value. So I'll do absolute value, and I'll do 2 to the x minus 8. Notice that we have no clue how to do the antiderivative of this. So now I'm going to do 1/2 of vars, y vars function y1 of 0.8 plus vars y vars function y1 of 0, and then times 0.8. And you know what I'm going to do actually to make this easier on myself putting into the calculator? Notice that every single one of these quantities has a 1/2 times 0.8. You guys see that? So since I'm adding them all together, I'm just going to put it all out front. And then I also noticed that, hey, I have 2 0.8s, 2 1.6s, 2 2.4s, and 2 3.2s. So when I type this into my calculator to make my life easier, so I'll do 1/2 times 0.8 times, and then the quantity. We're going to do y1 of 0, and then plus 2 times y1 of 0.8 plus 2 times y1 of 1.6 plus 2 times y1 of 2.4 plus 2 times y1 of 3.2 plus y1 of 4. Again, notice 0 and 4 only get used once. That's why I don't have 2 times those ones. And I just press enter. And that should be my answer, 18.1-ish. As a decent check, what you can do here is we can just do this on our calculator also. So I'll do fn in 0 to 4 of y1. Now, I'm not going to expect my answer to be an exact match because this is only an approximation, but it should give me an idea if I am like way off. So notice the exact answer there is 7.4-ish. We got 18.1 our approximation. So we have a bit of an overestimate, which is probably not, which is fine. It's an approximation, so it's not going to be exact. What do you guys think? It's okay. And we'll do one more example and I think call this a day. What do you say? All right. So it says the velocity time graph shows a train journey. Use the trapezoidal rule to calculate the total distance traveled by the train. You don't need to do trapezoids the whole time. You just need to like chunk the thing into like shapes that you feel good about. So like that's the way I would chunk it. So I have like a triangle, a rectangle, a trapezoid, another rectangle, and then another triangle. You guys buy that? So I'm just going to add those things together. So the rectangle or the triangle, so that's 0.2468. So each of these are 0.2. So 1/2 base times height. The base is 0.2 and the height is 80. The rectangle, the base is 0.4 and the height is 80. The first trapezoid has bases of 80 and 60, and its height is 0.2. The second trapezoid has bases of 60 and 100, and its base is 0.2. My next rectangle has a height of 100 and a base of 0.6. And then our last triangle has a base of 0.4 and a height of 100. And then it's just calculator time. What do you guys think? So if you're given a graph like this that's piecewise linear, where like each piece is a straight line and they're just like attached together, you can always chunk it up into like a bunch of different little area problems using rectangles, triangles, and trapezoids. And even if you didn't remember the trapezoid formula, which for God's sakes will be given to you on anything you have to do, you could take those trapezoids and like break them up into like a triangle and a rectangle, even if you needed to. You know, like don't bother with it. Like you'll have the trapezoid formula, but if you don't remember like how to use the trapezoid formula or whatever, you can always just kind of chunk it into a rectangle and a triangle and it'll be fine. It's more additions, but that's the gist of it. What do you guys think? Not bad, right? In general, like, here's what I would say as far as calculus is concerned. From a practical standpoint, like, these integration ideas are easier than the derivative problems. From an actual calculus perspective, integration is way harder than differentiation because not every integration problem is even going to be possible to do. To get a numerically exact answer, there's stuff that you just can't integrate it. After learning like 4 or 5 derivative rules and like a handful of formulas, like you can differentiate anything. Even if it's like really complicated, like it stinks, it's like a lot of work, but it's possible. There's integration stuff that's even relatively simple that there's like, yep, there's no way to do that by hand. You can approximate it, get a really good approximation, but like, you know, don't have to work too hard to get something that's not integrable, which is a shame, right? But that's just kind of that way that rolls. So for next class, we're going to have our chapter, 11 quiz. Let's talk about what to expect for that. Again, I don't think it should be too bad. You really have like one integration formula that you need to be like competent using. So let's just type this stuff in real quick. So you should be able to find general antiderivatives. When I say general antiderivatives, what do you need to remember to include? Plus C, very good. Okay, you should be able to find specific antiderivatives given a boundary condition. What does given the boundary condition mean that you can do? You can solve for C, right? That just gives you a point on the antiderivative that allows you to solve for a specific C. Okay, you should be able to evaluate definite integrals. I should say really by hand and with a calculator. Oops, is that the wrong thing? And then yep. So the last type of thing you'll have on there is like an integration story problem. So I would give you like a rate function and ask you to, to do like an accumulation problem, like find out how much stuff, has accumulated or like you've lost given some rate function. So that's just really like 11.1 and 11.2. Yeah, like the water's leaking out of something, or like 11. This example 11.5 I think would be relevant, or this example 11.8 would be relevant. That's the kind of rate integration story problem we're talking about. Yep. And I guess as long as we're here and doing stuff, let's talk about the test too, right? Can't spell this morning.